So in the previous video, we were talking about double replacement reactions, or 2 videos ago. Double replacement reactions are when you add a compound to another compound. Now, when you add a pure element to a compound, this is called a single replacement reaction. So I notice I have magnesium reacting with copper 2 chloride. This is a compound. So when you add a pure metal or pure substance, not a pure substance, a pure element, there you go, to a compound, one thing is going to switch. Okay, so the magnesium is going to switch places with the copper. Then the copper would be by itself and the magnesium would be with the chlorine. Now, do all of these reactions happen? Anytime I put a metal into a compound, is it going to react? Well, no, of course not. There's some things that you can drop into acid and they don't react. There's some things that you can put into water and some things do react and some things don't. So how do you decide what is going to react and what isn't? When we were doing double replacement reactions, it was if it made a solid, it reacted, or if it made a gas, or if it made water. Now, if it's a single replacement, it is if the single metal that you're putting in is more reactive than the one in the compound. Okay, so the rule is a solid metal that is higher on this is the activity series or reactivity series, it will react or will replace with the metal ion that's under it. So what I do is I check the pure element and I check what it's going to switch with and be like, okay, is the pure element higher on the reactivity series? If it is, it will react. Now, you don't have to have this memorized. This is something I would give you as well. I would give you this reactivity series, okay? So I would be like, all right, I'm looking for magnesium and copper. Well, magnesium is up here and copper is down here. So is the pure element higher on the list? Yes, then it will react. So these are going to switch places and I will get now copper by itself and magnesium chloride. So the generic form is one thing plus a compound and the A and the B switch places. And that's what it's going to be. Now, again, whenever you make new compounds on the right side, you have to check your charges. Now, that's if you're making a compound. Okay, so for example, this AC, I do need to check my charges when I put them together. If I have a pure element, though, so this is my note about pure metals, hydrogen as the products, you put them in their standard state. So if I had started with like H plus on the left, if hydrogen is by itself, it's H2 gas. For example, if I have barium by itself, it's BAS. So you just put them in their standard state. They should not have a charge when they are by themselves. Now, again, this is for molecular equations. This is not talking about complete ionic or net ionic equations. There shouldn't be any charges in a molecular equation because everything should balance out. Some things are going to change charges. So because it was plus on the left does not mean it's going to be plus on the right. If it's a single element, they switch places and it's by itself, it should now have an oxidation state of 0. It should be the pure element. All right. So in example number 8, I want you to write the molecular and net ionic reactions for the following single replacement reactions. So remember, your molecular should not have charges. And then the net ionic should be, instead of it being what makes the solid, like in a precipitation reaction, in this case, it's going to be anything that was reduced or oxidized. Okay, now you could also write out the full ionic equation and cancel out the spectators, but if you don't want to do that, I would suggest going through A with me. Okay, so this is the one I looked at above. We got magnesium reacting with copper 2 chloride. Now, magnesium is higher, so they are going to switch places. So now I have copper by itself and magnesium with chloride. So one of the ones I put together, I did have to check my charges. Magnesium in a compound is +2, chlorine is -1. So I get MgCl2. And then copper by itself is just copper solid. Okay, it doesn't keep the charge because this is a redox reaction. So this is actually balanced. I'm good. I wrote over here that chloride was my spectator, and I know that because chlorine didn't change its charges at all. So the net ionic equation then is whatever changed charges. Well, I had magnesium solid. This doesn't have a charge. The copper, which is 2+ over here, was aqueous. I left out the chloride because it's the spectator. And then my products are copper solid with no charge and magnesium 2+, because over here it's in the compound, magnesium 2+ aqueous. So this is my net ionic equation. Notice, yes, magnesium is on both sides and copper is on both sides, but it actually is a different state of matter and a different charge. So this is the actual chemistry that happened. Okay, now if you look at B, I'm putting tin into iron 2 nitrate. Now, if I do this, first of all, will it react? So is the single metal higher on the reactivity series than the one in the compound. And if you check, we've got iron is here and tin is here. So tin is actually lower. So you just write no reaction. Then you don't have to do anything. It doesn't react. You don't have to write out the reaction because it doesn't happen. Okay, now down here, zinc is higher than hydrogen. Notice, yes, this is a reactivity series of metals, except for hydrogen is right here. And that's because a lot of things react with hydrogen. So they are going to switch places. So then hydrogen will be by itself. That's why I've got H2 gas over here. Hydrogen, when it is just hydrogen by itself, is H2 and it is in gaseous form. And then zinc will go with the chloride. So I checked my charges, I get ZnCl2. Okay, and then I balanced, I put a 2 here. Now again, net ionic is just the things that change charges. So zinc went from 0 to +2, so zinc has to stay in. Hydrogen went from +1 to H2 gas, so it also stays in. So this is my net ionic equation.